Good evening. I'm Elizabeth Long, the Sheridan Dean of University Libraries, Archives, and Museums at Johns Hopkins University. And it is my pleasure to welcome you to this evening's program, the second Wavelengths event at Hopkins Bloomberg Center, co-sponsored by the Frary Library and by Wavelengths, an engaging and outreach program that brings the work of Johns Hopkins researchers to public audiences. So the Irene and Richard Frary Library, which is just a few floors below us, is part of the broader Sheridan Libraries at Johns Hopkins that support faculty and student research across the whole university and the health system. This evening's slideshow, which we've now turned off so that it doesn't distract you during the talk, but we'll turn it back on during the reception, features books from our special collections that demonstrate humanity's long-standing fascination with exploring the ocean. We encourage you to visit our locations and browse our resources online to discover more about our collections and services. The Johns Hopkins Wavelengths program brings audiences inside pioneering discoveries and innovations that benefit people across the globe in critical areas of study, ranging from bioastronautics, cancer research, food systems, and science diplomacy. Through public events, narrative nonfiction books, secondary school lesson plans, digital communication toolkits, and exhibits that inspire, they are co-developed by leading Hopkins experts. Wavelength produces insights that spark conversations in dorm rooms, dining rooms, boardrooms, and the offices of leading government representation. The Wavelength books are available for purchase or as a free PDF download through an open access program by the Johns Hopkins University Press, Project Muse, and have been downloaded more than 200,000 times in more than 100 countries across the world. Dr. Bellingham's book is the 8th in the Wavelength series, with more titles in the works. So now I'd like to invite tonight's distinguished speakers to the stage while I introduce them. Dr. James Bellingham is the Executive Director of the Institute of Assured Autonomy and a Bloomberg Distinguished Professor of Exploration Robotics at Johns Hopkins University. For more than 30 years, he has been a global leader in the development of small, high-performance autonomous underwater vehicles, AUVs, resulting in a class of systems that now widely used within the military, industry, science communities. He has been instrumental in innovations for ocean observing and has spent considerable time at sea, leading 24 AUV expeditions in locations across the Antarctic, North Atlantic, Mediterranean, South Pacific, and Arctic. Prior to joining Johns Hopkins, Bellingham led robotics programs at MIT, the Monterey Bay Aquarium Research Institute, and Woods Hole Oceanographic Institute. As a globally recognized marine technologies expert and acclaimed inventor, his work has been featured in Medium, iHeartRadio, and NPR, among others. Nell Greenfieldboyce is a correspondent at NPR, where her reporting focuses on general sciences, from astronomy to geology. For more than 20 years, her news reports and features have been heard on national programs such as Morning Edition and All Things Considered, as well as on the podcast Shortwave. Prior to NPR, Greenfieldboyce spent a decade working in print journalism, during which time her work was featured in U.S. News & World Report, New Scientist, among other publications. She received her undergraduate and graduate degrees from the Krieger School of Arts and Sciences at Johns Hopkins University, so we are delighted to welcome her back into the Blue Jay nest for the evening. So our deep thanks to both of you for finding time in your busy schedules to make this conversation possible. Before we begin, I want to remind everyone to silence their phones. And with that, I turn the program over to you.
Well, thank you all for being here today. This is a super delight for me. I was incredibly enthusiastic when I was invited to do this, and I read this awesome book. I mean, I just feel like this is really well done. I felt like Jim was just sitting next to me, just talking to me. I feel like I already know you, having read the book. And I feel like if you want like an overview about like what's going on with ocean exploration and underwater vehicles, like going even back to like the 1880s and stuff, this is like, it's beautiful. It's perfect. And some of the writing is just so fun. Like you wrote that, I've lived to see our oceans become populated by robots. So I thought at the beginning, like maybe I could just put you a little bit on the spot and ask you, like, if you had to guess, like what's out there right now? Like how many little robots probably are wandering around the ocean by themselves? Like if you had to put a number on it.
If I had to put a number on it, well, so first of all, it depends how broadly we classify robots, because some of the systems that we build in the ocean sciences are actually pretty simple. Like, so there's a set of floats which really don't drive anywhere other than sort of make themselves go deep and go up and report the data back. And there's probably about 4,000 of those out in the ocean, which sounds like a lot, except when you think about the fact that they're supposed to tell us basically what's going on in this ocean environment, and that corresponds to about 2 data points in a patch of ocean about the size of California.
Okay, but they're like tethered or something, right?
No, they're not tethered. These are just free-floating vehicles that are kind of drifting with the ocean. So these profiling floats, they're part of the Argo program, they're called. Now, the propeller-driven vehicles are the type which I mostly work with. I would guess that there's probably there might be a couple hundred in the ocean, maybe a couple hundred in the ocean, because for the most part, those systems are operated for shorter periods of time. Right now, probably the most interesting thing going on with that class of platform is they're trying to find the Malaysian airliner again out in the Indian Ocean. And so there's a group of those vehicles out with that Ocean Infinity is operating out there looking for that platform. And then in between, there are these vehicles that kind of have the characteristics of both, right? So they have a buoyancy engine, so they can make themselves heavy, so they sink. They can make themselves light, so they float. And they have wings on them that takes that vertical motion and translate it into forward motion, and we call those gliders. And I would guess there's probably several hundred of those out at any given time. I know that the leading company there has probably built 4,000 of them. And so I guess the question is how many of that 4,000 are actually out operating? And by the time you get to that sort of number of vehicle, and those vehicles can last for weeks or months at a time at sea. So those types of vehicles, kind of if it's sitting in the lab, why is it sitting in the lab? Shouldn't it be out in the ocean working? You don't need a ship. That's the usual reason to keep things on shore, because ships are expensive. So those are probably out there in the hundreds, I would guess.
Okay, so hundreds of robots, right?
Yeah, hundreds of robots. I know it's not as many as we would like.
But that's a lot of robots. I mean, the ocean is big, though, right?
Yeah,
so
it is.
But okay, so you mentioned the kinds of things they could do. Like, what's the ones that are out there operating now? What's the kind of range of stuff they're doing? Like,
Yeah.
what are their jobs?
Yeah. So at the high end, right now, one of the things that we don't have are really good maps of the seafloor, right? So if you were to go and look at Google Earth and you were to look at a picture of the Earth and zoom in on the terrestrial side, you can zoom in and in and in till you see individual cars, right? In the ocean, if you zoom in, you're looking at sort of patches of ocean that are hundreds of meters on city blocks on a side. There's a very few places in the ocean where you're going to see higher resolution data, maybe at the scale of tens of meters, and that's very unusual in the ocean. So that means you miss a lot of the features that tell you about the geology, the biology of the ocean. And so if you really want to make high resolution maps of the seafloor, you do it with autonomous underwater vehicles. You do it with AUVs because they can get a sonar very close to the bottom, so you get very high resolution maps. And they can fly very nice profiles, very steady profiles, so your data quality is really high. So that's why they're looking for the Malaysian airliner with those class of vehicles. And then the other vehicles are really helping us understand sort of the physics of our ocean, the physics and the biology of our ocean. So how does the ocean circulate? How much heat is being transported from the ocean from low latitudes to high latitudes? it's a lot, but it varies, and we're really curious about why, what actually drives that, and whether we might accidentally turn it off, for example. That would be a bad thing. So those are all things that you really spend a lot of energy figuring out how to make your platforms as inexpensive and as long-lasting as possible, like the Argo program, or like the floats, which allow you to cover parts of the ocean which move faster, like the boundary currents. You get the ability, for example, to understand the California current system on the Eastern Pacific along the west coast of the U.S. And the Gulf Stream kind of goes a little too fast for the gliders, but in principle, you know, those are the types of things that you really don't get a good picture of from floats that you'd like to get a picture of, and so you use the gliders for them.
Okay, so that's kind of today,
Yeah.
right? Hundreds of vehicles out there doing things like mapping, doing some basic, you know, measurements of temperature, salinity, that kind of stuff, right?
And biology too, right? We're beginning to sort of equip them with biological sensors.
Like what kind of biological sensors?
Well, so the basics are actually, so one of the ways you tell biology is by measuring the chemistry. So if you measure uptake of nitrate, which is a nutrient, you know that there's organisms there eating the nitrate, right? If you see, and so nitrate and oxygen usually move opposite, right? So if nitrate is going up, oxygen's going down, and vice versa. And so you can kind of see the ocean breathing if you monitor those chemicals. And then the forests of the ocean are the phytoplankton, right? They're little microscopic organisms. They're the ones that are basically producing maybe half the oxygen we breathe, and they have chlorophyll in them, so they fluoresce. And so you can measure them with very simple fluorescence measurements in the ocean. So those are a set of the tools you use. And then bigger stuff is actually harder to see, right? You know, because they are more dispersed. And so you have the smaller it is, the easier, ironically, it is to measure, and the bigger it is, the more of a sampling problem you have.
Okay, so when you started in this field, you were a physicist, right? You got your PhD in, let me read this so I get this right, superconducting sensors that can detect ultra-low magnetic fields.
Yeah.
So you were not like a Jacques Cousteau kind of researcher. You didn't come at this from studying crabs or
No.
like urchins or anything like that, right?
Right.
So why, like back when you started, which would be what, like the early 1990s, right?
Okay, yeah.
Yeah, okay.
Well, actually, late 80s. I'm
Late
a little
80s.
older than that, yeah.
So the idea of like an autonomous underwater vehicle, that was kind of like a novelty idea,
Oh, yeah.
right?
Yeah.
So why were you attracted to this at all? Like you just saw an ad and you applied and you wrote that your wife was shocked and that your friends thought you were crazy? Like what?
Yeah.
You could have done like all kinds of other things with a physics degree. Like why autonomous underwater vehicles?
So it was an intersection of a number of things. So one thing that happened, ironically, was superconductivity had, blew up from a little field where a room like this, the audience here, it probably numbers more than the total number of physicists that did superconductivity in the world when I started it in graduate school. And then the high T sub C superconductors were discovered, and suddenly it was 10 times this much showing up at meetings. And I realized that I was going to be a cog in somebody else's big lab. And I really liked being in on the front end of things before they took off. So for me, I was very much looking for that. And the folks who had funded my PhD thesis were at MIT. They had been trying to get this underwater robotics group going, and they hadn't quite managed to get it off the ground. And the other little detail is I grew up moving around. So I grew up, my father was in the diplomatic side of things, and so we moved a lot, and I lived in a lot of very interesting places, and so I kind of had the travel bug. And so, when I saw in the Infinite Corridor this little advertisement looking for somebody to get this laboratory going, it was like, oh my gosh, that's what I'm looking for. That's what I want to do. And so I walked in and walked out with a job the same day, which turned out I should have at least talked to my wife, in hindsight. But.
So, but you talked about like, the travel part of it appealing to you, but initially you were just testing these vehicles like in the Charles River.
Yeah.
And like the first time you were invited to go to take this thing, the Odyssey, right? Was
Yeah.
that it? So this is like an early
Yeah.
version of it was autonomous, right?
Right.
Okay, so they wanted you to take this down to Antarctica, to this place where 3 continental plates come together, right?
Right.
And your whole lab was against this idea. Like, why did they think that was a bad idea?
Well, so this has to do with the fact that in the research world, you're kind of running a small business. So you have a laboratory, and you have to raise the money to pay for the students, the postdocs, the other engineers in the lab. And so that was what I was doing in addition to all of the technical things associated with the vehicle. And so in any business, right, you're watching that cash flow, and there's some point at which that cash flow hits zero. And what you're hoping, right, is that all those proposals you're writing are going to come in, and they're going to basically pick you back up again, and you're going to keep your whole lab going. And so that's kind of going on in the background of all of these academic labs. It's kind of what keeps the engine going, and it's kind of what keeps it good, right? Because in order to get that money, you have to be competitive. In order to be competitive, you have to produce results. So it's kind of an intellectual capitalism, right, in a way. And so in my case, what happened was I had a couple of big proposals that didn't get funded, and one of them I was sure was going to come in, but the whole division of the company that I was working with was actually eliminated. So that money there was no way that money was coming back again. And so there I was sitting in my lab with a lot of really great people, and we're making good progress on the vehicle, and it wasn't clear where the dollars were going to come from to keep things going. And Marcia McNutt walked in, and I had already been talking to Marcia, and Marcia walked in with the fact that this cruise had been moved. So there was a cruise going to the Antarctic. It was moved so that now it was going to be over Christmas and New Year's. And surprise to surprise, half the science party dropped out. And she said, if you're willing to go and stand science watch on the ship, you can take your vehicle along, and they'll give you a couple of ship days, and you can run it. And I thought, well, that sounds a little crazy, since we had just been running with it in the Charles River. And I went back to the lab, and the lab agreed that, yes, that was crazy. But on the other hand, I'm looking at the finances. And so it might be crazy, but, on the other hand, it's a roll of the die, but I kind of believed we could pull it off, so we decided we would go for it. And the lab pulled together. I had a guy walk in looking for a job, and I told him he could have a job as long as he was willing to go to Antarctica. He later became head of the Antarctic, the service side of the Antarctic program, so that kind of career move worked out okay for him. And we packed up a lot of parts and just shipped them to the ship. It was a 2-month cruise, so we spent the cruise kind of modifying the vehicle so that we could run it in that environment. We got a couple of runs in towards the end, and
you got it working. Although it sounded like at the end you were basically like hallucinating from lack of sleep. Basically.
Yeah, it was a pretty rough time, but it was also incredible, right? I mean. I had never been to high latitudes before, and the Antarctic just comes alive for that brief period of the Antarctic summer, and there's whales and there's seals and.
Well, have you been on any ship?
Oh, I'd been on ships before, but never. This was my first oceanographic cruise, so it was like starting in the deep end.
So how is developing a vehicle out in the field like that different than what you had been doing, which is like building it in the lab and then testing it in a murky river?
Oh my God, yeah, no, so it's completely different, right? When I did my physics experiments, right, I fabricated devices and tested them, and basically I would run hundreds of fabrication runs before I'd get a set that worked that I could use for my data set. In the ocean world, you take your vehicle and you put it in the water, and if it doesn't work once, it doesn't come back, and that's kind of the end of your career. Well, maybe not the end of your career, but it's not a good thing. So there was a lot more stress associated with the seagoing side, particularly when you're such a neophyte. And when I got on that ship, I really was a beginner, right? So
So you write about the ocean and how the ocean keeps its secrets, and I think you mentioned the loss of that Malaysian airline flight as being kind of a wake up call for a lot of the public that the ocean is so big and like something can just get lost in there and never be found again,
Yeah,
right?
yeah.
But in terms of like the challenges that the ocean provides in operating out there, I mean any vehicle really, but especially an autonomous vehicle. That's got to be down there by itself for weeks or months. Like, what are the main ocean challenges? Like, what are the main things standing in the way of the technology working? Like, what are you worried about most?
well, one of the things that people may not realize is because salt water is a conductor, radio waves don't penetrate the ocean. GPS doesn't penetrate the ocean. So all of the things that support a robot, right, when you're flying a drone around outside or you have your little Roomba running around in your office environment or whatever, all of the support for that, right, a place to go plug it in and recharge, that all goes away when you go into the ocean. So those are all problems that you as a robot developer have to solve. How are you going to talk to it? If you can't talk to it, how's it going to take care of itself? So it really drives you towards autonomy and thinking about how you make the vehicle. Making it think for itself is way overdoing it because we're not making it think for itself. But how does it respond constructively to the more likely scenarios, the more likely set of problems that it might encounter? And so that's a really large part of it is kind of coming up. And in the ocean environment, we do not have a silver bullet for communications. So what we have now that we didn't have then is we have some acoustic communications, right? What we had then was we had some long baseline navigation capabilities we can use, but we didn't have the onboard. There's systems now that we have that will measure the vehicle's velocity relative to the bottom if you're close enough, and those are super helpful for navigation. We didn't have GPS then, right? So there was no GPS, there was no Iridium, certainly no Starlink. So you had to kind of figure out how to make do without all of those, which really meant a lot of autonomy at a time when computers were 8-bit computers, right? They were really pretty small computers. I remember the first one when I tried to run floating point math on it, because there's a lot of the navigation means you have to take sines and cosines and trigonometry, that wouldn't run. So I had to make lookup tables for all the floating point calculations so that I could run it in fixed point. So those of you computer nerds will know this is like one step above a slide rule.
Well, what about like power, right? Like I remember I did a story years ago about an underwater vehicle that ran on like 5,000 D-cell batteries,
Yeah,
right?
yeah.
Like,
yeah.
I mean, if it's going to be operating for weeks or months, power must become a real issue.
Yeah, so totally. So we used a class of batteries which had been developed for torpedoes, which are silver zinc batteries, because lithium batteries weren't around then. But silver zincs are actually pretty close to lithiums, but a lot more dangerous. So they would catch fire. And so I had 3 battery fires, and battery fires are very scary things.
And what about sharks? You mentioned that one of your vehicles
Yeah,
was
we
attacked
got
by a
attacked
shark.
by a shark, yeah. A shark is not a problem. So you leave some teeth in the vehicle, but it gives you a good story. Battery fire, that's a bad news.
So what are some of the key applications? Okay, so like in like if we jump ahead like 10 years, what do you think these vehicles will be doing that they're not doing now?
Oh, wow, great question. So right now we're mostly doing pretty simple mapping type things with it. So not that that's simple, but making a good seafloor map is a whole sophisticated discipline, right? With special people who have survey certifications, and these vehicles are probably the high-end vehicles we use now. But what we're not doing is we're not doing autonomous inspection, for example, of offshore structures. We're not doing intervention or maintenance with autonomous vehicles in that environment. And when you think about the amount of infrastructure we have out there, I mean, currently it's mostly oil and gas infrastructure, and we all know what happens when that goes wrong. It goes very wrong, right? But you have other types of infrastructure as well. You have the seafloor cables, And we know those are vulnerable to bad actors. We have offshore wind, right? And there's a lot of offshore wind in certain parts of the world, and hopefully we'll be sort of off the East Coast here as well. But that has a whole set of infrastructure you have to maintain as well. And so the hope is that rather than go out there with a ship, which lowers a very expensive ROV, a remotely operated vehicle. So these are tethered systems that, you know, you're teleoperating. People are on the boat there usually running them, and usually at the cost of somewhere around $100,000 a day. So they're not cheap systems to run. You'd like that to be done with an autonomous underwater vehicle that doesn't need a ship. And there's a whole set of things that you might think of doing. You might think that that infrastructure out there already has power. So why not put plugs there so your vehicle could go plug in and recharge? May have comms, in which case you can use comms to download the data. So I think we're going to see a much more integrated infrastructure, which is frankly more robot friendly, and we'll be able to do things with our robots that make sure that that infrastructure is safe.
In your book, you talk about the BP oil disaster in the Gulf as being horrible, but also strangely conveniently located.
Oh, yes.
Like the ability to get ships out there and underwater vehicles to do inspections right there in the Gulf, like next to all these, you know, urban centers, is very different than you'll see like in the Arctic, for example.
Very true, yes. That's exactly right. And so many of the places now that we're talking about operating, you know, for you know, infrastructure operated, whether it's oil and gas operations or whether it's just a ship, right? The Arctic has no infrastructure, right, to support, you know, where's the Coast Guard based? You know, not in the Arctic Ocean, right? They got to go all the way around through the Bering Straits or wherever to get over there. So you're a long way from help. And so the first thing that people are going to ask is what the heck is going on and how much oil is going in the water and where is it going? Which were the questions that, by the way, took them the entire Deepwater Horizon. It took them better part of a year to figure that out. And now you've got to do it in a place where you basically have no access. So yeah, we have some, you know, if we're going to operate in these areas, we really have to figure out how to do this better and how to kind of solve the logistics problems, which means do it with much smaller, you know, more transportable robots. We used to call it the last seat in the helicopter problem. So the Coast Guard's going out there, they're going to take a bunch of people, they'll probably drop them on the ship, they'll, you know, try to figure out what's going on, and then you got one seat left in the helicopter, they'll let you put your robot in. And so you got to make a robot that, you know, is about seat sized. It isn't too much heavier than a person, and then can do all of these amazing things when you stick it in the water. So
I was also really struck by the applications for aquaculture. And, you know, I personally did not know that 50% of the seafood that humans eat is now a product of aquaculture.
That's shocking, isn't it?
It's a lot. And
yeah.
like, and you were pointing out in the book that like there are these sea pens, these vast sea pens where fish, you know, miles off the coast where fish are being raised, and just like what it would be like to have a fleet of autonomous vehicles able to measure water quality, you know, like take pictures of the fish to see if they're diseased or if they have, you know, how they're growing. And like, you know, I think that, and then, you know, we discussed deep sea mining, right? Like there's just tons of science about, you know, what goes on in the deep sea that could be affected by mining operations, and, you know, just a lot of very basic science questions still about the deep sea. I mean, I was pretty impressed, like, you know, you mentioned that back in the, you know, 1880s or whatever, the Challenger expedition was able to collect life forms 2 miles down. I mean, that's pretty solid for the 19th century, right? But still, there's so many questions about what's going on down there.
Yeah, I think, you know, in a way you could sort of think about the 20th century as being the century when we really kind of came to grips with the physical ocean. Right, you know, first we understood the large circulation systems, and then, you know, satellites came out. We started realizing how much more was going on at the mesoscale, that there were these kind of storm-like structures and eddies, and that the ocean was nowhere near as smooth as we thought it was when you drive a ship from, you know, one side of the Pacific to the other, and you take your cast, and it just all looks so nice. And you look at it in detail, you realize the more detail you get, the more you realize that there's things going on at smaller scales. And we figured that out in the 20th century. Well, this century hopefully is a century we figure out the biological ocean. You know, who's there, who's eating who, who's doing what to who, right? How do they respond to environmental change? You know, as the ocean heats up, as it gets more acidic, who wins, who loses? How does that how does that ripple through the rest of the ecosystem? You know, all of these things are just massive surprises. I think I tell the story in the book about, you know, my time at Mbari, right, where I arrived there as a physicist, and I think the ocean consists of water molecules and salt. And I'm around a bunch of microbiologists who, you know, are telling me, no, actually, come look through this microscope. And you realize the ocean's alive. And then I would drive them crazy, right? Because I had this microbe speech that I would give. And they would go, yes, Jim, we know there's microbes in the ocean. But, you know, the thing was you know, I read the science fiction story where these people, astronauts, go to a planet and the ocean's alive and it talks to them. And I thought, wait a minute, you don't have to go to another planet for that. Our oceans are alive. It might not talk to us in the usual way, but you know, we live on a literally living planet, and we don't understand it, right? We don't understand that part of it at all.
So what do you see as the major obstacles to, you know, sort of continued growth of the use of these vehicles, right? Like there's clearly tons of applications you could think of because the ocean is vast, it's hostile, it's hard to operate in, and you know, you could build all these little torpedo-shaped little automatic fish with instruments that you send out on your way. So
yeah.
like is there anything that you see as like you know, issues, showstoppers, concerns? Like what are the things that you think could stand in the way of this growing?
Well, right now, it just feels like a boom, right? It really does. It feels like the interest in the ocean is way up. You know, when we started Bluefin, when we spun Bluefin out, it was, you know, you could count the number of companies working in the fingers of your hand. Now, you know, probably if we do a 20-mile circle around here, there's many times that, right, just in this immediate area. So there's an enormous amount of entrepreneurial activity going on, in a lot of it driven by defense, but not all of it, right? Some of it driven by, you know, industry interest. Science, as much as I wish it were otherwise, science tends to be sort of, you know, tends to seed a lot of this technology, but kind of lives on the fringes of it, really, because the science dollars, if you've been on an oceanographic vessel, right, it's pretty bare bones, right? You know, you go on board, you know, some of these other vessels, and they're pretty well kitted out, even other countries' oceanographic vessels. So, but yeah, I think we're, I kind of feels like we're off to the races now. As a matter of fact, in writing the book, one of the things that I kind of had to come to grips with was a lot of the things I'd been telling people about vehicles weren't controversial anymore. And that was really annoying because, you know, it's like, I just lost you.
Right, like so going for like arrays of many smaller vehicles versus like big functional, like
yeah,
one
everyone's
big.
like, you know, I know it, Jim. We'll do lots of vehicles. I'm going, yeah, good idea.
Yeah. Well, it's interesting. You mentioned the role of the Navy. I mean, obviously, the Navy has played a huge role since, you know, World War I and anti-submarine technology development, right? And so they have their own set of needs and interests, which aren't necessarily the same as that of the scientists. I mean, you know, you said that at one point you predicted that kind of like every university would have their own little fleet of mini research subs. Like, does that still seem plausible, or is it, or is just the cost and the operation beyond? You know, I mean, you see people doing stuff with drones now all the time. But
Yeah. I think that, you know, getting things to sea and having them operate at sea, I think what's more likely is you have a few organizations that run vehicles, and then you're a scientist, you get a vehicle, you buy a vehicle on your grant, and then you give it to this operating organization that goes and deploys it for you. So I think that's a model that looks like that. And then you have your own little private oceanographic vessel, right? So you can get to wake up in the morning, and you get to check in, see what data it got, and decide where you want to send it next. It's pretty cool when that happens and it all works, you know, and we can do that.
So let's talk about other planets now. So, I mean, one of the things that I think is striking is that some of the places that NASA thinks are most interesting in terms of looking for potential life are icy worlds that have oceans. Maybe they're under 15 miles of ice, but there's an ocean
Yeah,
with
yeah.
ingredients that seem conducive to life. So, I mean, if you had to make a bet, like, what would you bet that our first true evidence of life elsewhere is discovered by an autonomous underwater vehicle?
Ooh, wow. Yeah, that's a bet I'd like to make. Yeah, I'd give you even odds on that.
Would you? Would
Yeah,
you
yeah,
make? Yeah.
yeah.
Because I mean, it seems like a lot of the things that are being worked on now here on Earth, like these, vehicles that have, chemistry labs to look at environmental DNA,
Yeah,
right?
right,
Like,
right.
you could see how that is easily very applicable. I mean, what would, other than getting through the ice, which is not trivial,
Right.
like, what would be the difference between operating a vehicle on, say, Europa versus the Indian Ocean?
So we had a meeting about this. So when I was in my Woods Hole period, I went through an Ocean Worlds phase, which I'm still in. So we pulled together a group of experts from NASA, from actually APL Johns Hopkins, I was at Woods Hole at the time. Of course, I ended up there later, but from a whole range of academic institutions, and we talked about exactly these types of issues. You're right, getting through the ice is like number one. And if you operate vehicles in ice-covered oceans, that alone is a different kind of vehicle operation than any other vehicle operation, because the usual get-out-of-jail-free card for a vehicle is drop your drop weight and go to the surface. So if things are going wrong, you have an escape. You have escape hatch, and you go to the top. Well, under ice, ending up stuck on the bottom of the ice isn't always a rescue option. So you have to figure out how you're going to get things back to that ice hole. And so getting back to the ice hole becomes sort of job number one, or you've lost the vehicle, and perhaps more important, you've lost the data on the vehicle and maybe the samples the vehicle took. So I think under there, you have to think about how you're going to navigate. You have to think about how you're going to communicate in an ocean, by the way, which you don't really know the composition of, right? So our ocean's composition enormously determines our ability to communicate and navigate. And so there's a lot of really tough questions to answer there. And then I think the other thing that you find will be a question, well, actually, here's an interesting one. It turns out that Earth is kind of the big dog in our part of the system, right? So you got the moon going around it, right? So the circulations in the ocean are really driven largely by the Coriolis force of the Earth. On these icy moons of the big gas giants, the dominant force is the gas giant there. And so all of the circulation structures are around the axis of rotation around the gas giant rather than the axis of rotation of the moon. And so you get completely different circulation physics in these icy moons in ways which I am not even going to attempt to explain. I just looked at them and go, that is weird, right? So these are things that are just totally different. And the physics part, we kind of know how to calculate those things. But the biology part, where would you go live? Probably hydrothermal vents. So you probably want to find those hydrothermal vents, at the bottom of that ocean, which is how deep we don't really know. And then you want to get down there without losing your ability to get back to the ice hole. And how deep is it and how much pressure is it? We don't want to crush our vehicle. There's a lot of questions.
But you think it's technically doable, though?
I hope in my lifetime, but maybe by the end of a century. So yeah. I mean, I think that what's going to happen, right, is I think eventually on the space side, we will start sending factories out, to that part. So instead of this cycle of we discover something with our spacecraft around, Jupiter, and then back on Earth we build a new spacecraft to ask the next question, and then we got to send it out there, and then we got to slow it down, which is non-trivial, and then we do a new experiment, and then, another 2 decades later, we get to send something out there. Well, what if we just send a whole bunch of parts there and some 3D printing stuff, right? And when we have a new question, we build a new spacecraft out there, and it's already there. So I think that's what makes a lot of sense to me. So.
All right. Well, I think we're going to open this up to questions. Maybe I'll go back and forth. So we'll start here with this gentleman, and then we'll find someone over on this side, and we'll go back and forth that way.
Thank you, Jim. Yeah, I'm a ringer. You and I are cousins. I'm a Hopkins faculty here in this beautiful building. I am working in our environmental sciences and policy programs and energy policy and climate, so I'm a program coordinator within those. And I'm a marine biologist.
Oh, wow.
And I'm a manned submersible pilot. So I still have a bias toward humans going down as opposed to AI, but I'll be convinced it's important. No, I think what you're doing is fantastic. And I have spent the last 25 years working in Cuba, where there are some of the healthiest reefs left on the planet, coral reefs. Wow. There are many threats, but one of the threats that I'm sure you've heard about is the spread of the lionfish, which is an exotic species, beautiful fish originally from the Indo-Pacific. They become engorged on reef fish, and fish, you know, the small juveniles, and fish are part of the fabric of the ecosystem. If you take the fish away, as we've seen in overfishing, the coral reefs die. We put divers in the water. Sorry, this is a long question.
Maybe,
but
is there a question?
yeah, it's coming up.
I have a question. It makes me wonder if we could use vehicles to destroy these lionfish.
That's my question.
That's what I was thinking. Like
that is my question.
Little underwater laser warfare or something.
Yeah, so there is a guy, Colin Angle. He was the founder of iRobot, one of the founders of iRobot, who actually took that project on. And so in his iRobot days, they were actually building little lionfish catching. I think they would kind of stun them somehow. They would stun them, and then it had like, it was a giant tube. It sucked them into the tube. And I guess these things are edible, so there's a whole market for eating them. And
it would just have a camera that would identify them by machine learning or something?
Yeah, this is probably, I want to say 6 or 7 years ago. And unfortunately, iRobot didn't fare so well, and Colin's off to other things. So I don't actually know what happened to that. But yeah, I mean, to do that, you have to really bring that robot cost down, which is kind of why iRobot was such a great company to take this on, right? You know, they were the ones that made a household robot affordable, right? The Roomba. So, you know, they really understood the sort of economy of scale. So I was pretty hopeful. Maybe we should give Colin a ring after this and find out what happened. Yeah.
All right, one on this side of the room. You, sir, had your hand up, I believe.
I was wondering, have the exponential changes in computing and chip power impacted what your imagination can do underwater with autonomous vehicles as much as they seem to be doing with autonomous vehicles on Earth?
Yeah, so the answer is you can do amazing things now, you know, in these, but you're really kind of limited. Like almost all of the AI today is trained by some pretty spectacularly large data sets, and that's kind of one of the things we're really sort of missing in the underwater environment. So we haven't really done a good job of collecting and curating our data in a way that we can use it for training these systems. And so that's something we have to solve, actually. So I think now there's other aspects of this that don't involve the environment. And so one of the things that I care a lot about, so we were talking a little bit about the stress associated with putting a vehicle in the water and just hoping it comes back. And by the way, every once in a while not coming back and then spending, you know, a week or so looking for your vehicle. I have a lot of sea stories about lost vehicles. I like to say that I've never lost one. I've only misplaced them. So, but these are things that we need to be able to give the vehicles the ability to solve problems on board the way kind of a human would, right? Rather than pre-programmed, because when things go wrong, you tend to get a failure cascade. It's not one thing, it's a series of things. And so that's the thing where that's kind of within our control. We engineered this system. We can build digital twins of this system. We should be able to train for that. So I'm kind of hopeful that some of the big impacts will be in reliability. And so certainly I have a bunch of graduate students working on that right now. I know it's not as exciting as some of the other problems, but I just want them to work, right? And I want them to come home with that data set. And you know, if we can use all this compute to let us, you know, build less expensive vehicles, then that's a big win. The LLMs, though, run on a lot of power, right? And so one of the things you do to make vehicles that last a long time is you make them power misers, right? So I have friends, like I have this friend, Al Bradley at Woods Hole, who's just a genius at making low power electronics. I used to swap stuff with him. So he would build stuff for his vehicle, and I would say, I want one of those. And you know, he would come up and he would go shopping in our lab, and so we kind of swap stuff back and forth. He was a big Star Trek fan, so if you ever saw a vehicle labeled, was it NC 1701? That was Al Bradley's, and that was Al Bradley's vehicle. But yeah, so I think on the reliability side, I think that's where it'll win. But we have to figure out how to make it low power. So.
All right, I said I'd go to this side of the room. So the lady in the brown shirt.
Sure. Thank you so much. Hi, Kate, former Hopkins alum as well. So nice to see you guys on the stage leading this discussion. Just very quickly, I have actually a few questions that are kind of tied together. You mentioned that there were a couple of hundred of these AUVs roaming the ocean floor at this point. Is that just US owned, or who owns these? Like, what countries are leading the effort? Are they academically owned, et cetera? Tied to that, you know, is the US cooperating with other countries on sharing data? I don't know if you're able to speak to that at all.
Yeah.
And are there any efforts right now to maybe set a standard, like set standards or norms or rules around how these vehicles operate in the ocean, akin to what we're seeing in terms of space governance?
Oh, wow. Oh,
So who owns these vehicles, first of all?
yeah, so in the U.S., a fair number, well, when Deepwater Horizon occurred, it turned out that a large fraction of the vehicles that were mobilized to go there were actually owned by oceanographers. You know, either oceanographic, and so we sent, I was at Mbari at the time, and we sent our vehicle down there. Now, most of those were actually funded by places like Office of Naval Research. So they were kind of bought by the government, but operated by oceanographic and academic laboratories. Today, there's a much bigger defense side to this. So the U.S. has a very strong, it's kind of it's the country that kind of really came out in a big way for these vehicles first, largely really because of O&R funding, I will say. So I mean, honestly, I owe my career to Office of Naval Research. They took a chance on me when everyone else thought this stuff was totally stupid, including NSF, by the way, turned all my proposals down. You know, the Brits have a very impressive program with a class of vehicles that started out as Autosub. There's a kind of hysterical naming story there, Bodie McBoatface, which the Brits have kind of a sense of humor when it comes. It turns out do not hold a naming competition in the UK. So the Germans do a lot of seafloor observing. So they do observatories which you put on the seafloor. The French have an ocean agency that runs a vehicle which they actually bought from the Canadians. So there's a Canadian company, ISE. There's a big effort going in China. I used to go visit there and sort of visit with those. I haven't been back there in probably a decade or so. But I know from the publications, if you were to look at the literature today and you were to look who's publishing on AUV technology, you would think that the entire world is populated by Chinese AUVs because they totally dominate the literature currently in the technical space. And a lot of this stuff is increasingly defense-driven. So it is true, South China Sea in particular.
And what are the rules of the road? Like, it's the laws of the sea? Are there rules?
So we have a framework, if you will, for where you're allowed to go, right? If you're in a naval vessel, if you're a commercial, if you're doing commercial activities. So the EEZs, we have now a executive order which has a structure in some respects kind of similar to that. I think there's people in this room who are probably much better than I probably at answering this question. But this is an area where, like, as an oceanographer, when I went to go work in Norwegian waters, I had to get approval from the Norwegians to operate in their waters. And the Norwegians are pretty easy about it. If you try to go operate in Japanese waters, Japanese are pretty hard, right? Pretty hard to get approvals to operate in their water. Certain things like those floats, so sharing data. So there are, in the meteorological side, people kind of figured out long ago that sharing meteorological data was good for everybody. And so the ocean a little bit has kind of that philosophy as well. So the Argo program is actually an international program. The US is the biggest partner. I think the French are the next biggest partner. And the deal is, if you buy one float and stick it in the water, you're a member. And you get access to all the data. And truthfully, you can go get all the data anyway, because it's all there on the web. So the US tends to put its data. As a matter of fact, if you put a proposal in, you have to commit to putting your data out there within, I think it's 2 or 3 years. I can't remember. It's been a little while since I had to do one of these. You have to put it out. And for that, and there's a couple of organizations like NOAA that run large data repositories. So I can tell you, I just spent a weekend with Claude writing a data access tool for oceanographic profile data, and in like a weekend, I generated a better data portal than I would have in a year before. So I have to say, one of the ways AI is really helping us write the tools to make a lot of this data more accessible.
But in terms of international relations and sort of like global, the sea is a global resource. I mean, is there anything issue that's particularly
sticking point?
Yeah.
Big sticking point is on economic use of the ocean, right? So I remember visiting. I was the Woods Hole representative when they had the 25th anniversary for the Indian National Institute for Ocean Technology, and they had a lot of seabed mining equipment there. The reason they had seabed mining equipment was because China had come down and started exploring in the Indian Ocean. It's international waters, so there's no reason they can't. But India kind of felt like, you got the entire Pacific, and so you come to the Indian Ocean. So they kind of, we better get our act together. So there's a lot of potential competition around access to resources of the ocean. I think that's shaping up, and we don't have a lot of things like the law of the sea, which of course we're not signatories to. But a lot of those, they kind of have big blank spots. They go, oh, okay, you got to fill this in. You got to come up with an environmental protocol. They don't really give you prescriptive answers to that. And so how that gets filled in probably is it gets filled in by the first country that goes and does it. And if the first country that goes and does it isn't the US, it's going to be filled in by whoever else, probably China, right, as they work their way through the system. So it also greatly affects investment, right? Because if you're in a country where there's a lot of uncertainty about what's going to go on with this, you're not going to see industry investment in it. So I think in the book I talk about this, a lot, right? The robots are a two-edged sword. On the one hand, they're really helping us understand the ocean much better. They're helping us hopefully understand where the resources of the ocean are. They're helping us understand how to manage them better, hopefully. But they're also making them more accessible. And how we use that is kind of up to us, right? It's not really a science question. So.
All right, I said I'd come to this side of the room. So there's one back there.
Hi. I was curious about how you would perform something like, I'm familiar with when a company wants to develop industry like offshore wind or a tidal turbine, they have to do an environmental impact assessment, and that usually is very location based. And I've been seeing startups sort of talk about putting fleets of autonomous monitoring vehicles out on the water, but I haven't seen a lot about what kind of environmental impact assessment autonomous vehicles have to go under before they can be deployed. So I was curious if you had any information on like what the protocol for that is before they can actually be out on the water.
Yeah, so a lot of times autonomous vehicles are part of your environmental protection protocol, actually, is kind of the way it works. So if you're doing something where you're going to be driving piles into the ocean and generating a lot of sound, you have to demonstrate that you're not going to affect marine mammals or sea turtles. And how do you do that? Well, you got to know where the marine mammals are. How are you going to find the marine mammals? Well, one of the ways you do it is you put acoustic listening devices on gliders, actually, and you run gliders around out there. Now, for vehicle permitting of vehicles, I used to have to do this when I was on the West Coast because at Mbari, you're right next to a national marine sanctuary, and so we had to get all of the approvals. And so I did a blanket approval every year for vehicles, and the big thing that they were worried about was acoustics. And so the basic story was I went through and I figured out all of the different sonars that were used out in Monterey Bay, including on fishing boats and, you know, kind of everything that was out there. And the basic story is the vehicle sonars were, first of all, very high frequency, and second of all, not very loud compared to what you would have on a fishing boat, for example, that's trying to image, you know, fishing schools at greater depth. So I actually didn't have any problem getting permitting there. I can tell you the things that I had major problems with, and it wasn't really my job to do the permitting, but I would show up and carry the institutional flag at permitting hearings when we put a cabled observatory in. And so a cabled observatory is going on the seafloor, and so there's seafloor impacts. And boy, let me tell you, that cost us, I don't know, $2 million. I don't remember how much it was to get we put a cabled observatory out of Monterey Bay. And one of the things we put on it was a hydrophone so that we could listen to what was going on out there. It's actually a super cool hydrophone. All that data's online. So John Ryan runs a fabulous website. But yeah, the cabled observatories were the big challenge in the permitting space. Other things probably should be permitted and aren't, by the way, but.
All right, I think I see there's some hands like way in the back over there. You guys can arm wrestle for it.
Of the many marine robots that you said were in the oceans, what of them, in your opinion, would you say is the most important?
Well, of course mine. So I would say that from a understanding the planet perspective, honestly, a lot of the work going on out at Mbari, so Chris Sholin out there developed this device called the Environmental Sample Processor, and it's a device that sucks water in, it extracts the marine organisms from them, and then extracts the RNA and DNA, and does a molecular detection, right, of the DNA and RNA of the organisms out there. And so it's by being, and one of the things that makes microorganisms so very challenging to study is they're so incredibly variable, right? So if you make 3 measurements in a row and you see entirely different signatures, is that because the microbial population changed? Or is it because you're just sampling in a different place? And the answer is it's probably, if you haven't been careful, you're sampling in a different place. So this whole process of understanding these little microbes in the ocean, which, by the way, each one of them is a chemical factory, and they're transforming, the chemistry of the ocean would be completely different, right, if you didn't have the microbes in it. And so all my Mbari friends, if they see this, are going to, there goes Jim again, telling the microbe story, but it's true. I mean, they're really important, and we don't understand them. So here's a great story, right? We used to run these prediction experiments out in Monterey Bay, and we could usually predict when the bloom was going to occur, so when the microbes were going to grow. But we could never predict which microbes were going to grow. And every once in a while, they wouldn't be there. And then we had this thing where we were trying to develop a docking system, and we were running a vehicle around with a camera on it. And when we got it back on shore and we looked at the camera footage, it was like the footage was full of sea nettles, of jellyfish. These are like 6-foot-long jellyfish. And they're basically vacuum cleaners of the ocean, right? They're sweeping it. Go, maybe that's why there's no microbes sometimes. Maybe they grew and the sea nettles came along and ate them. And believe me, we don't have anything on any of our vehicles that will tell you that those jellies are there. So there's whole pieces of the ecosystem we're just not sensing. So it's the biology, really, and I'm a former physicist, right? So I'm telling you those, the biology is where the action's at.
All right, another question on this side of the room?
Hi, good evening. You mentioned just recently position and relative to where the microbes are, and you've also mentioned position and navigation and being able to look at the floor when you have proximity. But when you don't have proximity to the floor, what are the promising technologies for knowing your navigation, knowing your position in the ocean?
Yeah. So this is one of those things where you kind of have a toolkit. So I teach a marine robotics design class. And it's like, I wish I had something like GPS that just works everywhere. We don't, right? So it's a little, so if you're going to be operating in a defined area, then the method that gives you the best navigation is you basically put down acoustic beacons. And you can kind of usually, the ones that are most commonly used, you can kind of sense them out to maybe 10 kilometers. And they'll give you a navigation, a range accuracy off of them of about a meter. And so if you have enough of them down, and I know I'm 5 kilometers from that one, and 2 kilometers from that one, and 1 kilometer from that one, I can figure out exactly where I am. So that's one thing. But a lot of times, that's not what you want to do, right? You want to operate over a larger area. And so there are methods of measuring your velocity, and there's two problems that you have, right? One problem is knowing which way you're pointing. So that turns out to be surprisingly hard. And then the other thing is knowing how fast you're moving relative to planet Earth, right? Because if you take an inertial navigation system, it measures all the accelerations, it integrates them to get a velocity. But if you're not zeroing out that velocity measurement, you get a drift. And that drift just accumulates over time, and so you get enormous errors. So the question is, how do you zero that out? So there is a device called a correlation log, which was developed, I think, back in the 60s or 70s. Which will work for giving you velocities higher off of bottom, because it doesn't require the directional beam that the Doppler system does. The Doppler system works better at higher frequencies. Higher frequencies are absorbed by seafloor and or seawater, so they have to be closer. So sorry, I can get really technical here, but yeah, that's kind of some of the pieces we have in our toolkit that we work with. And of course, if you can go up to the surface and get a satellite update, that's how the gliders work. So. All
right, one more question maybe?
My first question was going to be, I thought I heard that General Mills sponsored Alvin or something back in the day, and I was going to ask you, this is actually not my real question, but if there was like a really exotic place where we could find funding to do this work, that's like cereal companies. But my actual question is, there's some project that's looking at like breakthrough technologies where if you imagine the Hubble, we put like $1 billion into something and it pushes the whole field further, like the Large Hadron Collider. And I kind of wonder, like, if I gave you $1 billion, Jim.
Yeah, where would I put it?
Like, yeah, what would you do to move the field?
I think that right now, honestly, and I'm a vehicles guy. I built underwater vehicles. I stick propellers on things. Sensors. It's all about the sensors, right? If I can make my sensor lower power, and then I can make everything else on the vehicle cheaper. I can make my vehicle last longer. It's all about, and so that's why we know so much about the physical oceanography. Physical oceanographic sensors are really good. We measure temperature to 1,000th of a degree, and they use like milliwatts, right? To make that measurement. So I think, if I had sort of equivalent measurements, so instead of doing that eDNA measurement, right, in 20 locations, through my 2-week vehicle run, if I could be doing that kind of continuously, that's a very different world, right, than the world I'm in now. And chemistry, right? Chemistry, there's a few things we can measure. We can do pH, we can do dissolved oxygen, we can do nitrate, which is, by the way, kind of expensive, but power-wise, 7 watts, right? So I know all of those power numbers, right? So those are things that you really, if that was 1/10 of a watt, right, we'd have nitrate sensors on everything. And the physical oceanographers would let them put us on the Argo floats, which currently they won't do because they're all about how many profiles do you get out of an Argo float? If you stick a nitrate sensor, it goes down to single digits. So you really, the sensor, and then the fidelity of the sensor, right? So for example, methane. I'm very interested in the Arctic Ocean. I haven't talked about this, but I have a set of colleagues who've worked a lot up there, and there's a lot of methane locked up in the seafloor. As the Arctic Ocean warms, the permafrost in the Arctic seafloor is melting, it's releasing methane. How much of that makes it to, and methane, by the way, is a really strong greenhouse gas. So how much of that is making its way to the atmosphere? A lot of it's probably getting eaten by microbes, right? And what are and we know that this is occurring, right? Because there's a fellow, Charlie Paul, who goes up there and maps, and Dave Caress, they go up there and they come back and they find there's these portions of the seafloor up there that have collapsed. They're the size of city blocks and they've dropped hundreds of feet. So that means something melted and came out of there. So we don't know any of those things, largely because we don't really have, all of the sensors that we have to do that either are in a laboratory environment, we got to take a water sample and take it back, or they're not very good sensors, right, that we can run in the ocean environment. Maybe they're drifty, maybe they're high power. And so the sensors are really the place where you kind of blow the doors off of the possibilities. And start being able to build lots of small, cheap vehicles and really answer these questions in a big way. So.
All right. Well, in another 10 years, we'll see you back here for how advanced marine sensors are changing the world, hopefully. Thank you all so much for coming. And thank you, Jim, for a lot of food for thought. And I think there's maybe some actual food, too, as well.
I was going to say, yes, we have some actual food. So, yes, thank you so much to both of you for a wonderful conversation. I'm so pleased to discover that we have $1 billion back here, ready to fuel science. So we do have a reception here. I wanted to let you know that Hopkins at Home has been recording tonight's discussion. And if you gave us your email, we will be following up with a link to that when that's available. And if you have a copy of Dr. Bellingham's book with you tonight, he will be happy to sign it. If you want to purchase it, you can do it through the JHU Press website and get one later, but then you won't get a signed copy from him. So thank you so much for coming.